Hello everybody. Today we'll be seeing an introduction to the subject Probabilistic Graphical Models. This subject has been introduced to the computer engineering students of Mumbai University in the semester 5. So let me take you to the brief background of what this subject actually tries to indicate. What is the motivation for designing such a subject or taking such a subject into consideration? Let us take the first example of medical diagnosis. So whenever a patient goes to the doctor for diagnosis of any disease, the doctor has to go through or see many different possibilities of a person getting affected for a disease. For example, he has to check many symptoms. He has to also go through the different case histories. He has to ask the patient to go for many tests, and then he can confirm whether the person is getting a disease or no. So as a result of that, I mean to say here is there are many different possibilities that the doctor has to explore before concluding that a person may have probability of a disease or no. Let's take the second example. This is an example from image processing. Now for an example, we take this into consideration that from the image, if we ask our system or our model to determine what is exactly present right now in this image. Now this image is a combination of a cow and grass which is green. So this is something which we can see with our naked eyes. But when we are training our model to do this will be actually present inside the system in terms of few pixels, few RGB pixels, and your model has to be intelligent enough to find out at what position the cow is there and at what position the grass is there which is greener. So these are few of the things that based on the type of applications our model keeps on changing. So this is where probabilistic graphical models come into the picture. The next example we can take here is when a mobile robot needs to synthesize data from all its sonars, cameras and other sensors to conclude where in the environment it is and how to move as to reach its goal without hitting anything. So it's the third case study where it gives us an idea that when a user is interested or when a robot is interested in moving at a place without hitting anything, so what all things it needs to take into consideration before going forward, right? So one could write special purpose computer program for every domain one encounters and every type of question that one may wish to answer. So if I am handling medical domain, so I may write a program or an algorithm which will answer all the queries of the medical diagnosis purpose, but it will not be able to solve the image processing issues. Same way, if I am working in the image background, I will be writing an algorithm which will be able to segregate the image as we saw there from cow to the grass, right? But it will not be helpful in robotics. So as a result of that, if our application changes, significant changes may be required to the program. So this is a gist of why probabilistic graphical models can be used, which will create a general model, and then based on our application we can design the model as per our convenience. So if we check, when we are talking about a general model, there are few things which need to be taken into consideration. First of all, one is representation, the second is inference, and the third is learning. So what is exactly representation? In a computer, we construct a model of the system about which we would like to reason. Okay. Then, key property of declarative representation is the separation of knowledge and reasoning. Okay. Knowledge is the knowledge base which we create for our system. But reasoning is, why are we adding this if A tends to B? Why are we adding this A tends to B to the system? That is where reasoning comes into picture. So just having knowledge for one system to get trained is not enough. We need to add reasons. And when we are adding reasons, at that time comes 2 or 3 different dimensions where probability comes into picture here. Representation has its own clear semantics separate from the algorithms that one can apply to it. So algorithms are separate and the representation is separate. Representation is inside the model, right? An algorithm will be for answering us the queries with respect to that model. We can improve our model for a specific application domain without having to modify our reasoning algorithms constantly. So as per our needs, we can model or we can improvise our model for a specific application domain. But we do not have to model every time the algorithms, because algorithms are abstract ideas which are just going to accept the input and give you the output back. So we do not have to model the algorithm specifically, but we can just, constantly keep on improvising our model. So if we go for the, you can say the abstract architecture of probabilistic graphical model. So it is in this way, where we can say that we have a model. Inside the model, we have something known as declarative representations. And this model will be hit by an algorithm. And this algorithm, now there are various algorithms if we can see over here. And these algorithms will be able to answer the queries. But for designing the model, we will always require an expert. Just say for example, we know that if we are going for a medical diagnosis system, even if our algorithm or our model says that yes, this person is COVID positive, we have to cross verify it with a doctor whether our model is giving us the correct answer or no. We can directly just cannot conclude. So there will be a domain expert always with respect to that domain. As I discussed previously, 3 domains like medical background, then image processing, then I have discussed regarding the mobile robotics, right? So as per the given domain, there will be few domain experts. These domain experts will be adding to the knowledge base of the model. And then using the representation and the various algorithms, we will be able to get the queries as per our requirement. So probabilistic graphical models is a framework for dealing with applications which have significant uncertainty about how the classification is correct. So this is the major role as to uncertainty, because we cannot be certain regarding any idea, right? Today it's going to rain, tomorrow it's not going to rain. I cannot be certain regarding such things. So when I am not certain, there comes the question of probability, no matter how clever the algorithm is. Probabilistic graphical models use a graph-based representation as the basis for compactly encoding a complex distribution over a high-dimensional place. Now, the thing is that when we say probabilistic graphical models, so what does it actually conclude? Probabilistic gives us an idea of how we can include statistics into calculation of predictions, and graphical is since we have complex relationships available, we can represent these complex relationships to the user in a graphical format, which will be more lucid for the user to understand. The nodes correspond to the variables in our domain and the edges correspond to the direct probabilistic interactions between them. Let us take an example over here. So if we check this example, if you see the first example, it gives you an idea of Bayesian networks. So in the Bayesian networks, if we see, we have the graphical representation of a complex relationship, let's say a medical diagnosis system. On that, we have calculated the independencies, then we have factorized, and then we can come to a conclusion that whether a person or what may be the probability that person may get flu or a hay fever, etc. So this goes as the basic of probabilistic graphical models. So as we discussed that representation, which is the first important thing. So this type of representation provided by the framework should be transparent. That is, a human expert should be able to understand what this representation is actually indicating us. So for example, if we see this graphical representation, this is very much understandable by any expert. If it becomes opaque, the problem is it cannot be easily explained, or even it can give us some undesirable answers. Moving on to the next variety, that is inference and learning. So inference is any abstract hypothesis which I usually create. Okay, for example, if I say that today at 11 o'clock it's going to rain, so this is an inference which I am trying to create, and this inference I'm creating from the knowledge base which I have, right? So PGM allows construction of real world models, whether by a human expert or automatically by learning from the data. How am I actually creating the inference? It's from the knowledge base as also from the learning. If I am not training my model properly, my model is not learning anything, so definitely it is not going to always give me the correct output. So as a result, my inference may go wrong. So basically, there are two types of experiments, that is deterministic experiments and random or probabilistic experiments. Deterministic experiments are those experiments for whom the outcome is determinable. That means it is either yes or no, it's either 0 or 1, something like that. Random or probabilistic experiments are such type of experiments in which although we have a finite outcome, but the outcome may not be yes or no or 0 or 1. It will give you a probability. Let's say there is 33% chance that India will be hit by COVID, third wave of COVID, right? So this is a probabilistic experiment. If it is a deterministic, if it would have been a deterministic, so it would have told that India will get hit by third wave of COVID or no, right? So at the end, we come with uncertainty. We just see what's uncertainty. So as we say that entire thing of probability or PGM goes behind uncertainty. So this is because I have partial knowledge of the world. I do not know everything regarding a concept. So I will always have a partial idea. Noisy observations, whatever we read or whatever we listen, we tend to take half of that and half of that we tend to forget. So as a result of that, whatever we are observing is noisy. The data is noisy. So as a result of that, we will not have a complete idea of how to work on. Phenomena not covered by our model. We can create model, which will be belonging, let's say, just an example, a patient's true disease is often not directly observable and his future prognosis is never observed. So if we say that there is a patient's disease and he is having cough and cold. So I have created a model which will say that, okay, if a person is having cough and cold for 5 days, so I may conclude that this patient is having COVID. But let's say this patient is coming and telling me that, okay, I have cough and cold, but I am not showing any other symptom of COVID. So as a result of that, my model is not that trained to find out all the various possibilities that a person may have cough and cold in case of any other diseases also. So that is somewhere related to uncertainty. Thus, to obtain meaningful conclusions, we need to reason not just about what is possible, but also about what is probable. So whenever we design a model or whenever we try to find out any outcome, so what are the possibilities? We need to work on that. That is very true. But we also need to work on what are the different probabilities of that event occurring. So this subject is entirely regarding this. In the next class, we will go into few basics of probabilistic graphical model. This was just an introduction. We'll see more basics into probabilistic graphical models as to how we actually try to design the models. Thank you very much.